Okay, this is the Group 4 Lab 6 digital motor controller presentation. There's a quick video of everyone in Group 4. Moving on to the agenda, we have the introduction, experimental details, experimental procedures, discussion, and finally the conclusion.
My name is Hiroki Ashima, and I'll be going over the introduction. The purpose of this lab was to understand the function and application of an Arduino board, a motor, and the Arduino IDE, along with other components such as LEDs, resistors, and potentiometers. The goal of this lab was to build circuits, troubleshoot any problems that came up, and use the data and schematics to analyze how each component functions in different circuit setups. The first set of experiments involved using the Arduino, LEDs, resistors, and a push button. These experiments focused on controlling the LED, turning it on and off, activating with the button, and programming it to follow a specific sequence. In the next set of experiments, a DC battery, motor driver, and a DC motor were introduced. The aim here was to control the motor's activation with the button, reverse its direction, and adjust its speed using the code. The final experiment added a potentiometer, which provided user input to control the motor speed. By translating the potentiometer's output into a PWM duty cycle, we were able to effectively regulate motor speed based on user adjustments.
My name is Jason Martinez, and I will be going over the experimental details. Starting off with the components and tools, Table 1 shows us the complete component list for the whole lab, and then Figure 1 shows us the Arduino Uno board. Moving on, we have a more detailed view and breakdown of the components and tools needed for each experiment. Let's go over the circuit schematics now. So we have 3 total circuits here. The first one being for experiment 2.1 through 2.3, and then the second one being 2.4 through 2.6, and finally the third circuit used for 2.7. Moving on to the description of each circuit. The first circuit is the most simple. There are 2 series resistors, each in series with an LED bulb, and then a push button is added. The button is in parallel with the pull-down resistor, and then connected back to the 5-volt output pin on the Arduino Uno board. The second circuit adds on to the first, adding the L298N motor driver, a DC motor, and finally a 9-volt battery. The driver board is connected to the Arduino via 3 new pin connections on the output. And then the third and final circuit builds off the last 2, adding a potentiometer to the 5-volt output pin. This allows the user to control the voltage going to the motor driver. Moving on to resistor selection. The series resistor was calculated with the following equation. The 220 ohm resistor was selected because that was the only resistor in our kit that fell within the range. Moving on to the pull-down resistor, it is calculated using the following inequality. We selected a 100,000 ohm resistor since that was the largest resistor or the greatest resistor value available to us. Moving on to the Arduino, it interacts with the push button in the following way. The button is connected to the Arduino output pin, and then the sketch reads the state of this pin, either high or low, high being the button is pressed, low being the button is not pressed. It does this using digital read of the pin number that the button is connected to. And then the input value, high or low, is used to determine what action the Arduino should perform. Moving on to the LED is connected to an output pin on the Arduino board, and then the sketch assigns a value high or low to that pin using digital write with the pin number followed by the value, high being on and low being off. And finally, moving on to the motor, a motor driver is needed, which is connected to the Arduino board, and then off of the motor driver, the motor and 9-volt battery are connected. The Arduino sends a PWM value ranging from 0 to 255 to the driver using analog write of the pin number and the PW followed by the PWM value. The PWM value determines the speed of the motor, 0 being fully off and 255 being the maximum speed.
This is Aiden Shu, and I'll be presenting the experimental procedures and results. With all the equipment and Arduino IDE open, start by building the following circuit on a breadboard connected to the Arduino, which is connected to the computer by USB. A green LED is connected to the ground and also connected to a 220 ohm resistor to digital pin 8. This code is compiled and uploaded. Set green LED to 8. For setup, pin mode pin green LED, which is 8, is set to mode output, where pin mode configures a specific digital pin to operate as either an input or an output. Then we have this loop. Digital write the green LED set to high, and we see that the green LED will be constantly on in this experiment. For the next part, add to the circuit a red LED which connects to the ground and also connects to a 220 ohm resistor to pin 7. The switch PB is connected to pin 4 and also a 100k ohm resistor to ground, and finally 5 volts on the Arduino. You can see here in the code that this is defined 7 for output input. Next, repeatedly run button state equals digital read PB, where button state is a variable declared up here, and digital read PB returns high if the push button is pressed, low otherwise. In this conditional statement, if button state equals high or when pressed, turn the red LED on, else keep it off. For the next part, keep the same circuit set up. Assign the components to the pins, and these pins are configured to operate as inputs and outputs. Like last time, if the push button is pressed, execute what's inside the conditionals. Turn green on, delay 2000 milliseconds, turn green off, delay 500 milliseconds, etc. Else, if not pressed, have both LEDs off. Down here, last B state equals button state, so that the last B state does not equal button state condition is false and doesn't run. With serial.begin and println, we can access the serial monitor and see PB is on when pressed. 2.4 introduces the DC motor and driver with 3 new output signals. Digital pin 9 goes to enable, pin 2 goes to in1, and pin 3 goes to in2. A battery is also connected with negative to ground and positive to the driver VCC. For the motor, negative goes to out 2 and positive goes to out 1. Note that the driver needs a jumper cap. In the code, dir A has value 2 for pin 2 and dir B has 3 for pin 3. The program starts with green LED on, red LED off. Variable digital val reads the state of the push button. If pressed, we see motor is on in serial monitor and the motor is enabled. Dir A high and dir B low means that the motor is spinning forward one way. Red LED turns on when the motor is running and green is off. After 2000 milliseconds, the motor is no longer running and the green LED is back on with red off. Serial monitor prints motor off. For 2.5, the circuit is the same. In the code, we start with green LED on and red off. Then digital val reads the state of the push button. If pressed, print one way, then reverse. Then run this for loop, start I equals 0, until I is no longer less than 8, with I increasing in increments of 1. Run the motor forward and turn the red LED on, green off. After 1000 milliseconds, the motor is stopped, red goes off, green comes on. After 500 milliseconds, the motor turns on again, but dir A is low and dir B is high, so it spins in reverse. Red turns on, green turns off. Then we repeat the loop. The loop runs a total of 8 times. After loop completes, the motor is stopped and lights go back to how they were at the start. For 2.6, the circuit is the same. Here we observe motor speed with duty cycle 170 and 40%. In this code and void loop, we use new variable button count to keep track of how many times the push button has been pressed, plus 1 each time. The code uses analog write to set the duty cycle with corresponding values 0 to 255. For button count 0, motor turns on, delay 2000 milliseconds, then turns off. After 5 seconds, the button can be pressed again for 70% duty cycle where the same process happens, but the value of the analog rate is changed. Here, the button can be pressed again for 40%. Then here, when the button count is greater than 2, the counter is reset to 0. Messages are printed when each case of duty cycle happens and button count reset happens. 2.7 needs the potentiometer, which is connected to the ground, analog pin input A0, and 5 volts on the Arduino. In this code, for ADC, we use analog read to read the voltage level on A0. This is in range 0 to 1023, and set to sensor value. Pulse width modulation needs sensor values to be converted to a range 0 to 255. For even button count values, motor is off. For odd button count values, the motor is on and spins forward at PWM value. The serial monitor is being constantly updated with analog input percent gain from the equation PWM value divided by 255 times 100. Finally, this conditional turns the red LED on and green LED off if over 75%, else green LED on, red LED off. The motor stops moving at around 10%.
My name is Anthony Chia, and I'll be going over the discussion and conclusion. One thing that went well was that when a circuit wasn't working, everyone in the group worked together to debug it. With more people trying to debug the circuit, the issues that arise can be resolved quickly. One thing that could have gone better was using non-faulty components. One of the L298N motor drivers was faulty. This was not realized quickly, and the time was wasted trying to debug something that couldn't be fixed. The component circled in green has a hole in it, which caused the circuit to function not as intended. The goal of this lab was to construct and test basic open loop systems using Arduino. In experiments 2.1 to 2.3, LEDs were connected to the Arduino Uno, while Sketch and the Arduino IDE controlled how the LEDs behaved. In experiments 2.4 to 2.6, a DC motor was connected to the L298N motor driver and controlled using the Arduino IDE software. In the software, a physical input like a button press can dictate the direction that the motor spins, how long it spins for before turning off, and the motor's duty cycle or speed. Finally, in experiment 2.7, a potentiometer was connected to dictate the motor's duty cycle or speed. When the potentiometer decreased or increased in resistance, the motor spun faster or slower. All in all, the experiments performed in this lab went well, except for a small setback with a faulty motor driver. One thing to take away from this lab is how the Arduino IDE and Arduino Uno interacts with other electromechanical devices.